Yeah, thanks for inviting or for offering the opportunity to talk about this. This is actually one of my favorite topics because it's something that's so interesting and challenging and has involved such a large number of people on the Diviner team trying to figure this out so we can make the most of our compositional data sets. But today I'll be defining the epiregolith and these thermal emission gradients that we see, and then talking about some of the lines of investigation we've been working on. So what is the epiregolith? So epi, outer regolith. It's defined by Wendell Mendel and Sarah Noble in 2010. They have this really nice LPSC abstract. If you haven't read it, I recommend checking it out. It's just under 2 pages, and they go through these 3 completely different lines of reasoning for why you need to have a special layer at the very surface. They look at optical photometry, they look at directional emissivity, and they also look at the thermal physical structure. And all of these lines through different means say that you have to have this at least 250 micron up to a millimeter thick layer that is extremely porous, perhaps with a Ferry Castle structure, in order to be able to reproduce all these phenomena. Because you have this very porous structure in a vacuum, it invites strong thermal gradients. So what we basically see is that on a particle scale, you have a difference in temperature in the surface. And because you have thermal gradients, and we're looking at wavelengths of light, and my internet connection is unstable, you get a wavelength dependent temperature effect. So if you're at a wavelength that's seen deeper into the surface, you're actually seeing warmer temperatures than you are at a wavelength that is not seen as deep. And so what we measure with Diviner or with any thermal instrument looking at one of these planets is not emissivity, it's thermal emission that has this wavelength dependence. And it's been observed for a long time. When they brought back the first Apollo soils and put them into special environment chambers back in the 1960s and 70s, they saw this immediately, and that's been reproduced up to this very day. There's a cottage industry of these experiments, and it's also been produced using thermal models, and we've observed it with Diviner. And one of the reasons why I wanted to bring this topic back and summarize it now is because there's about to be at least 4, if not more, new thermal instruments going to the moon. We'll hear about 2 of those missions today with Lunar Trailblazer and Lunar Vice this after lunch. So it's definitely something we need to keep in mind. All right, so here's a schematic of what I'm talking about here. If you're on an airless body, there's the potential for having this thermal structure that we don't see on terrestrial planets. So the lower left plot here would be a terrestrial planet where you have an atmosphere. The air or atmosphere allows the thermal energy to be conducted very evenly, and you have either 0 or a very weak thermal gradient. If you don't have that atmosphere to convect, then you're really only transmitting along grain boundaries. And if you have really angular particles like we have on the moon, those don't touch very efficiently, or radiation. And so what we take is a particulate, and you're basically turning it into aerogel if it's on the lunar surface. So you have this really highly insulating surface, which allows these really large temperature differences we see on the lunar surface, because of the highly insulating nature. So the plot on the right is showing what the same material looks like with the same preparation in 2 different environments. The blue is this terrestrial environment that looks very much like the inverse of a reflectance measurement. And then the black one, the black curve there is if it is in a simulated lunar environment. And because of this differential and thermal gradient, you see a much colder surface in the strongly absorbing vibrational bands, the Raustrahlen bands, and you're seeing deeper into the surface when you look at the Christiansen feature, which is relatively transparent. So this is what I mean when I say this isn't emissivity anymore, it's now spectral emission. You can kind of visualize it, thinking about this. If you look at charcoal or coals or ashes or things like that, you're seeing the top surface is actually cooler than the interior. And that's exactly what we're seeing at these wavelengths. Where if it was an isothermal surface, we'd be seeing the same temperature everywhere. And the strength of this thermal gradient is affected by a lot of different things. I'll talk about albedo and composition today, but it's also affected by packing density and particle size and other factors as well. And one of the critical tools for investigating this are these specialized environment chambers. I run one of these chambers at APL. It's called the Simulated Airless Body Emission Laboratory, SABLE. And it's a thermal vacuum chamber with inside it, we can control the temperature our samples. We illuminate them using both heaters and a lamp, and we create a lunar-like environment. We heard from Alessandro yesterday about a similar setup at DLR, and there's setups at Oxford, Stony Brook, Brown University, and soon University of Central Florida. But having these setups is really important for understanding these phenomena and how to interpret our data. One of the things we have been doing beyond just looking at mineral mixtures and simulants is looking at actual Apollo soils. On the left here are diviner data of all of the Apollo sampling stations, for which we have geochemical information from the return samples. And on the right are laboratory data of the reference soils that were collected at those. So these are the very uppermost measurements. And we see very similar trends. The y-axis here is iron plus titanium, and the x-axis is the location of the Christiansen feature, which is our primary compositional indicator in this wavelength range. There is a difference, though. You'll see there's a shift. This line here in the diviner data, it does not overlay the lab data. And this is expected because the lab data actually has the lamp at a 50-degree instance, while the diviner data has been normalized to a 0-degree instance. And this is one of these factors that we see when the solar illumination angle changes, that changes the thermal gradient and that shifts the spectral features. We have to take that into account. And one of the directions we want to go here is that you can see there's actually some diviner compositions that we don't have in our Apollo sample measurements, and so we want to get some of those too and see if the trend is continuing. One of the other things that was noticed was that if you take something of a known composition and make it darker, it also changes the location of this feature. And so there's experiments that were done by Catherine Shirley, adding carbon to different minerals and watching that Christiansen feature shift to shorter wavelengths. And there's a test here we can do with diviner as well. If there were a way of having compositionally independent albedo, would we see a similar effect? And we did see this because the optical maturity parameter is a form of compositionally independent albedo, and Paul Lucy was able to use this to come up with an additional correction and actually remove space weathering effects from the diviner data set. This was originally published in 2017, and recently we published an updated version as well. And then moving towards forward modeling, Parvati Prem at APL has been working a lot in this area and using optical scattering code and models that use very thin layers. So these are layers that are on the order of tens of microns, as opposed to the typical millimeters or centimeters you might use in thermal modeling, to look at the structure of this very upper surface and using optical properties with crystals that are measured with a bunch of different orientations as well. And the plot I wanted to point out here is actually the one on the right. These models would predict, as we'd expect, that in the Christiansen feature region, which is on the left side of this plot on the lower left, that you would be getting energy from deeper inside the sample than you would at the longer wavelengths. And we do see this. We're actually getting energy from 2 to 3 times deeper at 7 or 8 microns than we are at 15 to 20 microns. This is another case where we have the model that suggests this should happen, and we've actually seen it with diviner as well. So there's been a few times that we've been able to observe the moon in eclipse with diviner. This is some of that data. So the map here on the left is showing our orbit tracks going over the eastern part of Mare Humorum. And the time sequence here is that the initial orbits are starting on the right and they're moving to the left, and they're about 2 hours apart. So the first few here are when the moon was warm and normal, then it goes into the umbral eclipse and comes back out and then gets back up to temperature very quickly once again. And we actually saw that at the longer wavelengths, we had a warmer temperature in that first orbit after coming out of eclipse, because more energy was being deposited in that top layer, and the interior was actually a little bit cooler, which was a really nice observation. And then we reproduced it in the lab as well, where we let a sample cool off a lot and turned our lamp on and watched that same spectral region as we observed in diviner heat up first, and then equilibrate to the typical. So we're seeing these wavelength dependence as a function of the illumination situation as well. And then the final thing I wanted to mention here is composition. We know this is really important on the moon because the moon is made largely of transparent silicate minerals. But what we see in the lab when we look at minerals is very much exaggerated to what we see when we look at lunar soils, because lunar soils have opaques and meteoritic material and whatnot mixed in. when you start going to even darker things like carbonaceous chondrites, and this is some data that Carrie Downs and Hannah collected, the thermal gradient either is so strong that you're seeing past it at all wavelengths, or something else is going on because you don't see this, the shifts are not nearly as large. This is one of the great questions that we hope to be able to investigate with Bepi Colombo is Mercury so dark that these thermal gradients aren't setting up in the same way that they are in the moon? So in summary, we see these thermal gradients. We've been observing them through observations and laboratory experiments and models, and we're really trying to understand how all these different surface properties are affecting them. And there's a number of different ways in which we're continuing to work on this. One of the things we're really excited about is bringing in some machine learning techniques. And these are needed because of these additional new data sets that are going to be coming in just a few years. Thank you.